So, hello and welcome in this new series for BARC Interview Previous Year Question Answer Series. I will be solving those questions which are exactly asked in the previous year BARC interviews. So, get excited. Without wasting any time, I will be directly delving into the questions. So, I think that right now you can see my screen recording, right? So today we will be solving a question from heat transfer, and this question was asked in 2023, and this is specifically relevant for mechanical engineering guys and chemical engineering guys. So let me tell you the question. There is a solid pipe, solid not hollow pipe. That means it is having a constant cross-sectional area. That is, my area is not a function of x, or neither my diameter is a function of x. Okay, the length of the pipe is given as 3 meter, and here there is an extra distance of 2 meter. I will tell you that what is the significance of this 2 meter shortly. Now, here it is asked, draw the temperature profile from x equal to 0 to x equal to 5. Assume 1D heat transfer with constant properties of the pipe. So first of all, here it is given that only in this direction the heat is being transferred. So even if you are not given that it is a case of 1D heat transfer, you can always find that here it is insulated. Okay, that means there is no way of heat being transferred in this direction. Okay, and now here at this point, that is at x equal to 0, we have a temperature of T1 is equal to 200 degrees Celsius, and ambient air temperature is 20 degrees Celsius. So now you have to draw the temperature profile from this point to this point. And this is the significance of this 2 meter. Okay, generally in GATE examination or in any other, typical examination, you are asked to draw the temperature profile for this x equal to 0 to x equal to 3 meter. That is for this pipe. But now you have to draw the temperature profile for this extra 2 meter also. And you have to notice one more thing. I have written this T air at this position. That is far away from the ending position of the rod and not here actually. Okay. So there is another question, but firstly, I will draw this one. Clear? So let me go to the answer directly. Firstly, you see that I know that here my temperature is fixed and that is 200 degrees Celsius. Clear? And I know that at this point, my temperature is fixed and that is 20 degrees Celsius. So this point is my 20 degrees Celsius. So if I can draw a line that I am not drawing, so this is actually my 20 degrees Celsius. But I am not drawing this line because this will make the answer, make the drawing untidy. Clear? So now, how can I draw the temperature profile? And this thing is just the schematic of the bar, because I want to make you understand that here I have the bar. So honestly, if I just erase the bar, it will be good. Otherwise, the picture will be more untidy, but still to make you understand, I have drawn this schematic of the bar. So let me start. So here, up to this point, I have conduction in solid. So in solid, there cannot be any kind of convection. There can be radiation, but we are neglecting radiation in the solid medium. Generally, we don't have radiation in the solid medium. We have radiation in the gas or liquid. Okay. So here, only 1D conduction, and for that also we know that the area is constant. Area is not changing. So for this, I know that all of you already know, but still we have the Fourier's law. The Fourier's law states that my Q, the heat flux, is equal to K into dt dx into minus 1. So minus of dt dx. Clear? So now we have to draw it at the steady state. So if they are not asking you that to draw the time variation or any kind of thing, and they are saying that these things are constant. This 200 and this 20 degrees Celsius, these are constant. Okay, that means it is a steady state problem. Because I mean, if these boundary conditions are constant and also the thermal properties of this pipe is constant, then the temperature uh, profile also cannot change with time. Okay, so this is a steady state problem. That means in this problem, this Q will be constant. This heat flux will be constant. Okay, this is a constant. That means I will have my dt dx is equal to minus Q by K. So this is very easy, right? So up till this point, I will draw it something like this. Sorry, extremely sorry. This will be a straight line, right? This will be a straight line like this. Clear? So this is, or actually I should not draw it like this. This will be a, because, okay, okay. Now this temperature I don't know. Okay, sorry. This temperature I don't know. This is something between 200 and 20. So they can actually ask you. So just give the answer by intuition that here what can be the value of the temperature. So this can be somewhere like 150 or maybe 80 or maybe very less actually 50. Okay. So this is actually a gross assumption. This is not asked and okay. Now here, now from here to here, this is the main crux. That from here to here, what should be the temperature profile? First of all, we have to look for the media. So here, what we have? We have air, right? After the bar completes, we have air. So air is a fluid. And now here the temperature. So here I have any temperature T. Now this T is for sure is greater than 20 degrees Celsius. That means it is as good as having a plate having some temperature greater than 20 degrees Celsius and the ambient air is at 20 degrees Celsius. You have studied the case for natural convection for a vertical plate, and this is the same case. So this is what? Natural convection for a isothermal vertical plate. Vertical plate. Okay. So for that, what will happen? So let me draw it here. Now this is the case scenario. So let me just copy this part and place this here. Okay. So now what will happen? So physically here in the vicinity of the plate, the air will be heated and its density will be reduced, and because of the effect of the buoyancy, it will rise up. Correct? It will rise up. And this is the natural convection. So there will be what? There will be a boundary layer, a thermal boundary layer. Okay. After this thermal boundary layer, the temperature will be constant at 20 degrees Celsius. So I will draw it with this color. So now what I will have is that I have to draw this variation. So honestly, this variation is happening like this. I think that you have, if you are a student of mechanical or aerospace or chemical engineering or PI production, if you have studied heat transfer, the convection heat transfer, now you know that the temperature profile here will surely not be linear. Okay, this will not be linear. Okay, so you cannot draw it like this, because when you are drawing a linear temperature profile, they will ask you that is it a straight line or not? The moment you say that it is a straight line, that means you are sure that it will be a straight line with constant slope. Then you have to explain it. But do you know for sure that it will be a straight line? No. Better you draw it as a curve. Obviously, you don't know the exact equation of this curve also, but for sure it will not be a straight line. And also for sure, here it will be a smooth curve like this. Okay. Here it cannot be like कि ऐसा हो गया फिर ऐसा हो गया, ऐसा कुछ नहीं हो सकता. ठीक है. So this is the concept of conduction and mixed and natural convection. So the remaining temperature profile will be something like this. So this is 20, a straight line and joining by a smooth curve. Okay, so this is not looking good. So still it is not looking good. Sorry. Okay, now it is fine. So they may ask you to draw the boundary layer. The boundary layer will be something like this. Okay, after which the temperature is constant. So this will be the answer. This, what I have drawn. This is the answer for the first part. Okay, draw the temperature profile from x equal to 0 to x equal to 5. Assume 1D heat transfer with constant properties of the pipe. Now, the thing is, up till now, you might be thinking that, okay, ये तो बहुत आसान था, मुझे तो आता है. Now, turn the bar upside down. Now, draw the same thing on the same graph. So, what they're asking is that previously, the bar was like this in the horizontal position. Here, previously, the bar was like this. Okay. And here it was T equal to 200 degrees Celsius and T air is 20 degrees Celsius. Clear? Now, what you will do is, I will show it like this so that you can get it very well. So, I will copy this. So, this was your previous situation. Now, what you have to do is, you will turn it like this. So, it was like this, you have to turn it like this, upside down. Now, everything is same as that, okay? So, here at this point, I have T equal to 200 degrees Celsius and the air temperature is still 20 degrees Celsius. But now, the actual difference is that the gravity was like this in the previous case, the G, but now the gravity is like this, G, okay? So, now you have to draw the temperature profile from x equal to 0 to x equal to 5. You have to understand the x is still this axis. X is still this axis. Okay. So, what you have to do is, now you forget that this bar is here because this horizontal bar is not here. But you have to draw the t versus x on the same graph. You have to draw the t versus x on this same graph. That you have to draw. Clear? So, I think the question is clear. You had this bar, you have turned upside down like this. Okay, this end is at 200, this end is at, sorry, not this end, this air is at 20 degrees Celsius. You have to draw the temperature profile from this end to this end. Okay, and you will superimpose this temperature profile in the previous graph. So, let us do it. I think now it is becoming interesting and this is the magic of BRC. Okay. So, now what is happening is that, see, still what you have here the 200 degrees Celsius here, and now here you will have some temperature that is less than 200 degrees Celsius, and you have to keep in mind that still this is insulated through all the sides here, and only heat transfer in x direction is possible. So, now you have to understand that here obviously the bar will have again a temperature that is greater than 20 degrees Celsius. Now, this is a case of natural convection or a horizontal flat plate. So, this is a flat plate having temperature greater than 20 degrees Celsius and the ambient is at 20 degrees Celsius. Again, I will copy it and drag it actually. So, now you know that this temperature is greater than 20 degrees. That means the air here will again become hot, and because of the density difference, it will try to go upward. But now the catch is that the air will move like this. Air will move like this. That means this phase itself is creating the temperature gradient and thus creating the natural convection. But at the same time, this phase is hindering the airflow. This phase is hindering the airflow. This phase is hindering the airflow. If you study any good book like Senjel and Simbala, like the heat transfer book is something like Sengel and authored by any other co-author, or कोई भी अच्छा book तुम ले लो. If you see the comparison between natural convection for a vertical plate and the horizontal plate. Okay, for both cases, the plates are hotter than the ambient. Okay, and this part is solid. So the air will move like this. You will see that because the air is being hindered, the airflow is being hindered, and the airflow is what? Natural convection. Convection means what? Air is moving. Air is moving and air is dragging the heat along with it. That means if the air is moving with a lesser amount of velocity, that means the heat will be dragged in a lesser amount here. That means this case with a horizontal flat plate, the heat transfer will be lower. I think that I am able to convey you the concept. That is because the airflow is hindered, and convection means heat transfer augmented by airflow. So airflow is hindered, that means heat transfer is hindered, that means there will be less heat transfer. So this is the only concept that you need to understand. So now that means for the upside down case, now let me define that my Q1 is the heat transfer for the horizontal pipe, not bar, and my Q2 is for the vertical, okay, vertical pipe. Now I have already explained that why my Q2 will be less than Q1. Clear? Q2 will be less than Q1. So this is the now magic. But still in the bar, inside the bar, there will be only conduction, 1D conduction. So previously, if I see that my dt dx1, that is the dt dx for the previous case. So this was what? Minus Q1 by K. Now my dt dx2 is equal to minus Q2 by K. That means my dt dx2 will be less than dt dx1. This is the magic. So dt dx2 will be less than dt dx1 because my Q2 is less than Q1. So actually I need the mod. So I will take the mod here. Okay, I will take the mod here. So that means my slope will be lesser. So my slope will be lesser. I will draw it in with a different color. So maybe with blue. Let me draw it with blue. Okay. So let me just erase this part and let me change the color of these things so that you don't confuse. Okay. Okay. So I will also remove this part. So this black part, I am putting my legend. So this black curve is for case 1. So I will write it that it is for the horizontal case. Horizontal. Okay. And the blue curve is for the vertical case. Vertical case. So the blue curve will have a lesser slope up till this. Okay. Okay. This is fine. So up till this is having a lesser slope. That means this temperature will be greater. This temperature is greater than this one, and this slope theta is lesser than this slope theta 1. Okay, this theta 2 is less than theta 1. This was the main concept. Okay, and after that you have to understand that after that it will be, the final temperature will be still 20 degrees Celsius because the air is still at the 20 degrees Celsius. Here, but here now the magic is that if I have drawn the boundary layer theory, if I had drawn the boundary layer before, so if this is my boundary layer, okay, so this is my boundary layer thickness, so I can write this is my delta T1. So now can you tell me that what will be my delta T2? Will it be lesser or greater? You have to understand that there is a very simple concept. The temperature here is greater. It has to come down to the same temperature. It has to come down to the same to the same temperature, that means the boundary layer thickness will be greater. The boundary layer thickness will be greater. Okay. So it will have a boundary layer thickness like this. I will draw it by a red color. No, red will be, I think, confusing. So I don't have so many colors here. So this color. So this will be your, this will be your, there. This will be your delta T2. Clear? So if this is your delta T2, I cannot say that this is my delta T2 because here I have already this 20 degrees Celsius. Okay. So, sorry. So my delta T2 will be something like this. Okay. So this will be my delta T2. Anyway, I have to just say them that my delta T2 will be greater than delta T1. Okay. That means now it will be something like this. After that, it is constant, sorry, again, because final temperature should be 20. So, like this, final temperature should be 20. So, if I, again, I have to draw it in a good way. So, final temperature after this is 20, but now it will be some like this. Okay, now it is fine. So, another way to interpret this is that, see, this delta is what? This delta, the thermal boundary layer thickness, is actually like the thermal convection thermal resistance. More the delta, the less is the heat transfer. And here I have already proved that the heat transfer is lesser for the upside down case. So this is for the horizontal case and this is for the vertical case. So these things you have to understand. Okay. Now one more thing I want to say, I want to give you a homework. Okay. Now you have to draw the temperature profile for the case, So this is the case, but now I have a fan here. But now I have a fan here. This fan is rotating like this, blowing air in this direction, this upward direction, blowing air in this upward direction. So this is the bar, and here I have a fan which is blowing air in this direction. Now you have to draw the temperature profile for this thing. I will post this answer very soon in the YouTube community post. Okay. Before that, you have to answer this because this can be the bar question in this year. Okay. So now last thing, that in DRC, you have to take your confidence. In any interview, confidence is the key. Obviously, confidence backed by proper knowledge. Without knowledge, तुम कुछ भी कह लो वो तुम्हें बाहर फेंक। लेकिन जो भी कह रहे हो confidence के साथ कहना. Okay, you have to have that confidence. See, if you have told them कि मुझे लग रहा है कि बार upside down होने पर heat transfer increase होगा, because बार upside down होने पर क्या होगा, that we cannot very easily tell by mathematics. That we have to tell by experimentation and intuition. In the very good books also, they have talked about this thing by the same logic, that the flow is being hindered. There is a no hard and fast mathematical logic. You can tell them कि सर मुझे लग रहा है कि एयर ऊपर जा रहा है और अच्छे से उसके फेस के साथ टकरा रहा है, that means the heat transfer will increase. If you do this approach also, but still, obviously, if the heat transfer will increase, then the graph will be something else. If you draw the correct graph, I mean, you are giving some hypothesis, okay, and based on that, you are drawing the correct graph. Then also, you have a good concept that is proved, okay. So where you cannot have a solid mathematical logic, you can give your hypothesis, okay, but where you can have a solid mathematical or maybe some scaling logic, there you cannot give hypothesis. Like when you are saying that my heat transfer will increase, then you cannot draw this graph, this blue graph, then it is totally wrong. If you are saying that my heat transfer will increase, you have to draw like that. Okay. So up till now, this is over. This video is over. If you are liking this thing, if you are liking my teaching, please comment, like and share. Itna to banta hai na. If you feel that this guy is doing something for you, please subscribe this channel. And most importantly, give me your suggestions that what should I do about this video to improve this series, because I think that you will like this series. Okay. Please comment if you are liking it or not. If you are not liking it, then also you should comment. Finally, if you want to connect with me, you can connect with me in LinkedIn. Okay. So I will meet you with the next question in the next week. Until that, solve the homework. Goodbye, take care, and thank you.